Well, thank you everyone for joining again. I'm Eric Malmstrom, the CEO of SafeTraces, and today our webinar will be on planning and commissioning for ASHRAE Standard 241, applying equivalent clean airflow rate in real-world settings. So we are really privileged today to have a great panel, the authorities on this topic joining us. So our first panelist will be Dr. Bill Bonfleth, who's the chair of the ASHRAE 241 committee and a presidential fellow at ASHRAE. Also, his day job is professor of architectural engineering at Penn State University. Our second panelist will be Wade Conlin, who is the chair of the working group on commissioning, operation, and maintenance. And his day job is the commissioning and energy discipline manager at Hansen Engineering. And our third panelist is SafeTraces' very own Phil Arnold, who is a member of the ASHRAE 241 committee and worked on the working group for commissioning, operation, and maintenance. And well, all three of our panelists have deep expertise and experience on this topic from their involvement both in their jobs, but also their involvement in ASHRAE in the precursor to the standard and actually formulating and publishing the standard, which was quite a feat and happened just a couple months ago. So just a very brief context on why we're organizing this educational webinar. SafeTraces, for those who don't know, is a California-based company that does performance testing and commissioning in buildings using a novel aerosol tracer technology. We deal a lot in the world of building owners and industry practitioners who are both, we found, very excited about this standard, but then had a ton of questions regarding what it actually means. So understanding the standard itself and some of the details, and then understanding the logic behind it, and then also really focused on implementation of how do you actually put this standard into action in buildings. And so we saw a big need out in the market for better understanding this and hearing directly from the people who wrote the standard, because we want ultimately this now to go into real world implementation. So I think we have a great lineup today of speakers, and then also the content hopefully will be very useful. So our agenda today is to do an initial overview of equivalent clean airflow conceptually, and given its prominence in the standard, Dr. Bonfleth is going to go through that, and then we're going to have Wade and Phil go through linking the equivalent clean airflow to the planning and commissioning requirements, and walking through a couple case studies on how you would actually put it into action in two common settings, one a school classroom, and then secondly an ER waiting room in a hospital facility. So without further ado, I'm going to hand it over to Dr. Bonfleth, or Dr. Bill, and he will kick us off on this first section.
Hey, thank you, Eric, and thanks for the opportunity to be here and talk about Standard 241. We're in a big rollout communication phase right now, and this is part of it. And there certainly are a lot of questions about how the standard should be used and what it means. So I'm glad to contribute to that discussion today. So the fundamental concept of Standard 241 is equivalent clean airflow, just as much as the fundamental concept of standard 62.1 is outdoor airflow. So you've got to understand this concept, understand the standard, and everything kind of flows down from that. So let's jump right into the next slide. What's the status quo for air quality related standards? The prescriptive standards that we use focus on outdoor air. So ASHRAE standard 62.1 specifies outdoor airflow requirements based on how many people are in a space and on what the size of the space measured by its floor area are. And you can see a sample from the key table in standard 62.1 over on the right, and you see the people rates and the area rates there. To a much lesser extent, these basic acceptable IAQ standards address filter efficiencies, and in 62.1 right now it's a MERV 8, and they're generally very light in their treatment of air cleaners. You can certainly use air cleaners to comply with standard 62.1, but there's not much in the standard about how to use them, except that they can't produce ozone. That's the main thing that the standard says about air cleaners, and it's kind of a negative. Next. All right, so filtration and air cleaning versus outdoor air. This is one of the key issues in standard 241, and it's really why we use equivalent clean air, because there are big differences in energy consumption associated with equivalent levels of control of a given type of contaminant. And that's illustrated by this kind of busy table from an article that was published in the ASHRAE journal just this month by Marwa Zatari and colleagues. Marwa is also very involved in the development of the standard. So we're used to relying on outdoor air, and we think better air quality means more outdoor air, but that's the perception we're trying to fight here. And if you look at this table carefully, and I wouldn't expect you to read it right now, I'll pull out the key numbers for you. For outdoor air, the range of cost per CFM of outdoor air, depending on climate zone, ranges from 16 cents per CFM to $4.16 per CFM, while air being moved through a MERV 7 filter ranges from 3 to 16 cents per CFM, and with slightly higher pressure drop, MERV 13 ranges from 9 to 26. Now you have to adjust those filtered numbers by the efficiency of the filter, but the multiplier for a MERV 7 is only about 3, and it's only about 1.3 for MERV 13. So big difference in cost. Next. So what is equivalent clean airflow? Here's the definition right out of the standard itself. The flow rate of pathogen-free air that, if distributed uniformly within the breathing zone, would have the same effect on infectious aerosol concentration as the sum of actual outdoor airflow, filtered airflow, and an activation of infectious aerosols. So what we're trying to do is equate every control that we use for infectious aerosols to an equivalent amount of uncontaminated dilution air. And this is the fundamental concept of the standard, and you comply with it by using whatever combination of controls best meets your needs to meet the requirement for equivalent clean airflow. The only thing you have to do is have at least the minimum that's required by the basic acceptable indoor air quality standard, like 62.1 or the codes that reference it. Next. This figure illustrates a real simple example of equivalent airflow. So on the left hand side, we have a space that has a source of contaminants in it, S, and we have a filter that will remove it with an efficiency epsilon PR, and we're recirculating air through it at an actual flow rate VRC. So that air is going through, some of the contaminants are being removed, and the clean air, equivalent clean air that it's generating is going back into the space and controlling the concentration to some level CR. We can imagine an equivalent process over on the right, where we're simply bringing in air with no contaminants in it at some flow rate VACS, and we're exhausting an equal amount of well-mixed air from the space, maintaining the same concentration. So that value, VACS, is the equivalent clean air for that air cleaner, and we can easily show that it's equal to the efficiency of the air cleaner multiplied by the actual flow rate through it. And some other air cleaner and control types are more complicated to characterize, but all of them can be. Next. So how do we determine what these equivalent clean airflow values should be? I mean, we would do this the same way that we would do it if we were calculating outdoor air flows, but we now understand that we can do this in terms of equivalent clean air, and the process is very complex. I just want to say that I think one of the real accomplishments of standard 241 is the rigor of and the thoroughness of the analysis that led to to the development of these values. The flow chart on the right just shows how many inputs need to be filled in. We're using the Wells-Riley model. Some of the values are deterministic. We know the value, but others are distributed variables, like how much infectious material is someone emitting if they're infected in the space and they're at different stages of disease. There are lots of variables like that. We assumed SARS-CoV-2 pathogen characteristics. All of the things inside of that dashed green box are unique to each infected person. So we had to do a Monte Carlo analysis to get these values of ECAI. The goal was a very low individual risk level per hour. And for every space type that's in the standard currently, equal risk for all of them. And the units of ECAI are flow rate of equivalent clean air per person. Why do we do it that way? Well, for one thing, it's useful because it reflects the impact of the number of occupants in a space on risk. And also you can show, but we won't show here because of time, that individual risk in the Wells-Riley model, according to the assumptions that we used, is proportional to the flow rate per person. So not air changes per hour, not any other metric you may have seen. Next. So the one thing you know is going to be said about any standard that's published is that it's too complicated. But it's really not that hard to figure out what the requirements are for a space. So we have a number of occupancy categories for which equivalent clean air requirements have been developed. There are 25 space types under those categories, and they range from 20 to 90 CFM per person, doubled for loud vocalization. Very simply, you take the value from the table and you multiply it by whatever you want the population during infection risk management mode, the time when we're actually using the requirements of 241, and that gives you the total. That could be the design occupancy. That may give you a scary number that you don't think you can achieve. So if that's a problem, you can say we're going to have reduced occupancy when we're in a high infection risk situation. Next. This is the entire table that we have at this point, and there's not really anything to add here, but it's very simple and reminiscent of table 6.1 in standard 62.1. It's table 5.1 in standard 241. You can see the different types of spaces under the major occupancy type headings there. So we've got classrooms and offices and things you'd expect to see. So how does 241 compare with some of the other standards, and specifically standard 62.1 and the new CDC 5 air change per hour guidance? And I titled this slide apples and oranges. I suppose it should be apples, oranges, and bananas. There are three different things here. The first thing we should say is there's not an incompatibility between 62.1 and 241. They're actually complementary. 62.1 for non-residential buildings is a prerequisite for 241. 241 has an ECA basis, 62.1 has an outdoor air basis, and the rates don't address infection transmission. And as you might expect, the ECAI values are much higher on a per person basis than what you get from the odor and building generated contaminants values in 62.1. The touchy issue is this 5 air changes that CDC recommended all the time at about the same time that we published the review draft of 241. So the 5 air changes per hour is supposed to be a minimum for air quality that's applied all the time, where 241 only applies in infection risk management mode. The only thing I really want to point out here is that the carefully calculated values in 241 give us equal risk, and there's no claim that that's what you get from the 5 air changes. And in fact, if we look at the table on the lower right, you can see first of all that for 3 different common occupancy types that we're concerned about, indeed 241 has much higher values than the per person values in 62.1. But look at the air change rates. For an office, 30 CFM per person gives us only 1.1 air changes per hour with an 8-foot ceiling. A classroom, 40 gives us 10.5, and this is at default occupancy levels. And for a restaurant, it's 31.5. So there's really no relationship between air changes and risk, as we can demonstrate from the analysis we've done. Next. So to wrap it up here, so the rest of the team can get on with things. Equivalent clean airflow is a novel way of specifying control requirements, and we think it's a novel and better way of doing it. It puts outdoor air and cleaned or treated air on an equal footing and gives us their combined effect in one number, which is a very useful concept that facilitates cost and energy optimization of solutions. And the last thing I'll say is that this approach that we applied to infection risk can be applied to gas phase contaminants. It can be applied to particles. So it very well could become, and I hope it will become, the paradigm that we use for all air quality standards going forward. I think that's all I have, Eric.
Great. Thanks so much, Bill. That was very helpful. Again, it lays the foundation for what Wade and Phil are going to talk about right now. And then secondly, I think you just underscore how important this is for not only achieving the control of infectious aerosols, but also addressing cost and energy considerations. So thanks so much for that. Now I am going to turn it over to Wade and Phil to start talking about bridging what Bill just discussed to planning and commissioning requirements. So Wade, go for it.
Thanks, Eric. I appreciate that. I'm going to cover some of the intro stuff, and then Phil's going to get into something very specific that the overall team worked on. So initially we were called commissioning, and in reality, when we started looking at what this really dealt with, it was the assessment, planning, and implementation when you're looking at existing buildings. The standard does work with new buildings as well, but we're not going to cover those here from a standpoint of we're really looking at existing systems that we've evaluated. So all we're really doing is kind of applying the commissioning process, existing building commissioning process, but we're looking at it from an infection risk management perspective. So this was based on, and it's been extrapolated since, from the epidemic task force days. And the one requirement out of this, there's a handful of requirements, but you actually have to document what you've done or what you've evaluated, what you've implemented, what you've planned and implemented, and that's through the building readiness plan. It's a term that came up during the epidemic task force days, but in essence, if you already have an emergency preparedness document, or you already have a systems manual, or you already have some sort of operations manual that you're using, this information that, as we're talking about it, and any tweaks, changes, how things are supposed to operate, really truly need to be documented. And the reason is so that other people know what the systems are supposed to be doing, as well as occupants and others in there. So next slide, Eric. So Bill talked about the ECAI, right? So that's the volume of the equivalent clean air. We had a ton of fun with acronyms building this standard, just so you know. But from that standpoint, is the first one is the target, and Bill just showed you how to calculate that. Well, the goal of this is to figure out that target less what I have existing is a differential. If the differential in this case is negative, guess what? You're done. If the differential, as we found with most cases, is positive, it means that your target is larger than what your existing system is providing, and then you're going to need to make some modifications. So the target, just rewriting that equation here, and it's key, and we'll talk about it later, is that PZ IRMM is the people that you expect to be in that mode. And then for the existing, it's exactly what Bill just covered, just reiterating, it's your outdoor air plus the volume coming from your mechanical ventilation system, think of your air handling unit system, and then any air cleaning systems that you have, and natural ventilation. And so it's the grouping of all those items. So equivalent clean air of your existing is relatively easy to calculate, and we're going to show you some examples down the road. On the next slide, we're going to talk about the actual assessment phase of doing this work. And this is very much in terms of the assessment that you would typically do for a building, in terms of trying to figure out how the systems work. And we're doing it for infection control. So I am not going to read all these bulleted items to you, but from a standpoint of you need to understand the systems and equipment that you have in the space. You need to understand how they're actually operating. You need to understand that, so that potential separation spaces. That's if you have someone, like think of it in a school where you have someone who says, hey, I don't feel well, maybe I have something. Where you put them is a separation space, because you're going to have to treat that space slightly differently. You want to know how much ventilation you're actually bringing into the space. There's a couple different ways to look at this. What's written in here is that you're actually taking measurements of airflow. We're going to talk about another sample where maybe you don't have to take those measurements. You can evaluate how your system is working from that standpoint. One that I get dinged on a lot, or I get asked about, is coils. Why do I have to worry about the coils? Well, even though Bill just showed you that outside air costs a lot more than filters, it's not being removed as an option. You can increase your outdoor air, normal outside air, if that's what you would prefer to do. We don't think that's the typical mode that people will go, but if you're going to do that and you're going to consider that, you need to check your coils. As well as looking at how it's controlled, your ventilation system controls. If you've got demand controlled ventilation or you don't, how is that actually maintaining that outdoor air that you're talking about? And then also, you know, if you already have air cleaners, and then the different control strategies that go along the system. The goal here is to assess, to understand, what do I have? How is it working? What air am I getting? What air is being delivered? And that's so that you can actually start to actually do some evaluation or some planning, and then eventually implementation. So when we get to the next slide, which is planning and implementation, in essence, you've just described what you just discovered, what your minimum operating requirements are. So then you do that step. Do I need any additional equivalent clean air coming in from my spaces? So you do that same calculation, and most times that we see is that your existing system is not providing enough equivalent clean air. And so you're going to have to make modifications to your system. And we'll get into those modifications and what those can be a little bit later. So you select what those are, then you implement them, commission that they're working properly, or test that they're working properly, and then update your building readiness plan. Make sure that it's actually documented as to how it's going to work. And that's a really short synopsis of Section 8 within ASHRAE Standard 241. I think Phil's going to get into a pretty cool appendix that was built for this. Oh, sorry, I apologize. Cut myself short. There's a lot of different appendix that came along with our section. Appendix C, the tracer particle test procedure, that's what Phil is going to dig into. The building readiness plan, we have a template. The equivalent clean air calculator, we're actually going to use that to show in our examples later on. And then there's guidance, and this is essentially the guidance that was built during the epidemic task force by a number of people in terms of assessing energy recovery ventilators, because we do want them operating as long as they're operating safely from a standpoint of infection control, and then preventing re-entry of contaminated air. So those are different appendix. We'll take a quick peek at a building readiness template. This is very much a high-level sample. We also have another spreadsheet, and we're working more for the next version of the standard to have a little more detail, a little more information. But in essence, as you read through this table of contents, you're describing the building, when is it operating, how is it operating, what do I have for outdoor air, what do I have for filters, do I have any air cleaners, are they in room, are they in the unit, and then you talk about the assessment and planning, what you looked at. In terms of that assessment and planning, that is what you're planning to actually implement. And then also detailing out non-HVAC mitigation strategies. And we'll actually be an example, and we'll talk about that when we get there. And then in reality, you're just attaching a number of documents so that people can understand or look back at what was done. So this is a more formal version. There's a spreadsheet version that we also have that's a little bit higher level, but the intent is to still document all the information so that people know what you've done and how it's supposed to operate. And now, Phil, we'll get into Appendix C.
All right. In normative Appendix C, you're allowed to do an actual aerosol challenge test in the occupied space to prove the V volume of ECAI. And you do this by emitting aerosols into the space and measuring how quickly they're removed. This takes into account all the main characteristics of filtering the air, the passive and mechanical ventilation, filtration, deposition of the aerosols over time. They come out of the air just by themselves. It'll also capture natural ventilation like open windows and things like that, which is kind of hard to get with like a tab report. It doesn't measure pathogen inactivation. The aerosols are just challenge agents, and they don't have a way to mimic that. And this is all based on calculating the decay rate of the aerosol tracer particles versus the ECAI for the space. It's somewhat analogous to a tracer gas decay rate calculation, except that it's using aerosols instead of a gas. So it's a familiar calculation to many people. And it provides a pass-fail result, as we'll see in the calculator. I think you can go to the next slide. So there's a number of qualified tracer particles that can be used. At SafeTraces, we use DNA tag particles. Other folks have been very successful with sodium chloride particles, fluorescent tag polystyrene latex beads, and some occasions they use smoke or other particulate-based tracers. These are all allowed to generate aerosols and then measure the decay rates. The process requires two main elements. One is an aerosol generator, and it's a way to emit aerosols into the space so that you can measure their decay. There's 3 particle size bins that you measure, which is pretty normal. And those are covered in the ASHRAE standard 52.2, which relates to air filtration efficiency measurements. And then you have an aerosol detector. In our case, we use the one that's shown here and collect samples on filter cassettes. Other folks can use particle counters and things like that. The next slide, please. So the way you do it is the test is suitable up to about 900 square feet, and you put the aerosol generator in the center of the room, and you do 4 quadrants. I should have mentioned first, the test preparation, you have to select 10% of the high occupancy areas kind of by type. So like if you have conference rooms or break rooms or a gym workout area or something, these are all different types, and you have to select 10% of each of those different types and then go in and directly evaluate those within a building. If the rooms are larger than 900 square feet, you perform multiple tests in the room. So this quadrant-based system, you just block them next to each other until you cover the area of the room. You have to test it under steady state static conditions. Often we recommend that folks, set their supply air to more or less the maximum and manageable amount of outside air. You want to set up a condition that you could actually create to be used in infection risk management mode. So that has to be a steady static condition during the test period. You should not have aerosol generating devices active in the test space because they can increase your background readings. And then as we were saying, you have 4 quadrants, 4 detectors, and 1 generator in the beginning. It's actually pretty simple. You collect background information. So what are the particle counts at the background? So 5 minutes, check the particle counts, make sure they're stable. And then you emit the aerosols in that space, and you have to get the particle counts above 3 times the background level. So that's why you've taken the background, so you know where you're going. Generally speaking, you can do better than 3 times, but 3 times works really well. Then you wait for 6 minutes for the aerosols to settle and mix up nicely so that you get a good decay rate reading. And then you just monitor for the decay period up to 60 minutes, or when 90% of the particle count reduction is reached. That is 90% of the starting point versus the background. So you'll see the decay curve, and there's a whole there are calculations that are demonstrated in the appendix. They're pretty straightforward. They're kind of, as I said, analogous to doing a tracer gas kind of study. And the next one. So now we have a couple of case studies here we want to go into. The classroom. So what you'll find in infection risk management mode, the ECAI per person drives more difficult to achieve requirements in high occupancy density areas. So like a classroom where you have 30 people in it, you need to provide 40 CFM per person of ECAI. So that adds up to a lot. That's 1,200 cubic feet per minute for an 857 square foot conference room with a 9-foot ceiling. So what we found in this classroom is it was supplied by a HVAC system capable of putting out 1,500 CFM, of which about 370 CFM were outdoor air, and it had a MERV 8 filter in it. And the occupancy design here is for 30 people. So now we can take this information and apply it in the calculation that Wade had mentioned. And I think Wade's going to discuss how this works.
Absolutely, Phil. So this is a snippet of the equivalent clean air calculator. It's currently a spreadsheet. We're hoping in the next version it'll be a little bit more automated and more of a program, but this is the starting point. So on the first column is essentially all the information labeled as you would see it, giving units of measure because it's key for some individuals.
Mm-hmm.
And then you'll see this very first column is assessment. And so as you go down, we're dealing with a classroom. You have the target ECAI, which is 40. You're dealing with the area and the ceiling height. Anything that's a blue that you can see is a number that is expected that you would be inputting, right? So you've got the supply air and the total outdoor air, the numbers that Phil just talked about. And then you've got your design occupancy as well as your IRMM target occupancy. And then as you walk down through it, you are looking at your MERV rating of the filter and your air handling unit of source. Then you can get into whether you have UV in the HVAC or air treatment in terms of percent of CFM or air treatment in the space through CADR. And you plug those values in terms of what's listed in there, quantity and CADR, quantity CFM. Then you get down to the equivalent clean air per technology. And this is showing you how much air is coming from or how much air is calculated to come from the different technologies. And in this case, we've got a MERV 8 filter, which in the standard falls below the minimum. So you get 0 for that filter. The only contribution for equivalent clean air in this example as found is the outdoor air of 371 CFM. When you look at that, you look at it at a CFM per person to see if you passed to meeting 241. And in this case, it's a fail. And so this is doing that mathematically with the numbers that you found during your assessment. And then I think on the next slide, Bill's going to talk about testing this space through Appendix C.
Yeah, so you notice that this spreadsheet is all the same, and we've added the testing and evaluation, the aerosol testing part at the bottom. And during the test in this classroom, we've determined that there was 832 CFM of ECAI in that space, which when distributed over 30 students, it comes out to 27.7 CFM per person, and this is still a fail. And you'll notice that it's coming up about, I can't really read that, 360 CFM of ECAI short. So in this case, this classroom fails both on the calculation and on the aerosol measurement test.
So with that, you have to make changes, right? We talked about this. If you're short, you have to do something. And so this is the way it's just being framed, or the action framework to try and achieve that compliance, right? If you're compliant, you do nothing. We've just shown you that that's not the case here, right? When you're non-compliant, you can adjust engineering controls with your existing capabilities. So am I going to increase some supply air? Am I going to change my filter out? Am I going to open doors or windows? You can do non-engineering controls like we talked about, which is you can adjust or reduce the occupancy levels within. So that's that P sub Z IRMM. So instead of your design occupancy, I might use a reduced occupancy level. And then the third one is to make some capital improvements which includes, installing in-room filtration or UVC or a larger air handling unit or more than what the existing equipment can do. And so when you look at this, there's a lot of options, right? So there is no silver bullet. You have to look and do that. And so when we look at the next slide, you'll see the entire equivalent air calculator and how you would see it, which is through the assessment phase, through that third column, we've already shown you and talked about. And then in reality, after that, there's additional columns there so that you can look at different scenarios of how to get there, because we also know that lead time or distribution chain, supply chain issues still exist. So anywhere you see a gold highlight is where we've changed, and each column is its own scenario that Phil and I talked about in terms of looking at this. The first scenario is to reduce the occupancy from 30 down to 25 and to go to a MERV 9 filter. Let's say you had extremely old equipment and you weren't sure you could get higher, and you go, well, I'm gonna at least do a MERV or MERV 9A filter. When you get down to the bottom, you can see that through the calculation, it's a fail. And then through the testing, it
still failed.
It's still a failed.
Yep.
Yeah. And what this spreadsheet is doing, if you look down at that field system testing plus adjustments, because at this point we haven't retested it, we're evaluating to see. We might retest it later and we'll touch on that. But in essence, what we're taking is what was the airflow, what was the equivalent clean airflow of the previous or the base, and what have we added to it, and just adding that delta and assuming a value that amount of equivalent clean air gets added to it. Is it going to exceed that target, right? One thing you can also notice on that column, that the target ECAI is now actually 1,000 instead of 1,200. So it does actually change what you're trying to achieve. The next scenario is going to MERV 11 filters, right? Keeping the occupancy at 25, but going to MERV 11 filters, and that passes in the calculator. Phil, do you want to touch a little bit more on the testing and looking at that one, or?
Sure. Yeah, in this case, so the testing in that one is shown to be a little better because of the let's see, the effect of the on the MERV 11 you actually get a benefit, because on the MERV 8 you don't really get a filtration benefit in the HVAC calculation. So when you add up the values in there, you're getting a benefit from the supply air that you don't really see on the MERV 8 filters. If you look at the next column, we're using the tested results plus adding in some in-room air cleaners, in this case a HEPA filter of 100 CFM of CADR, 4 of them placed strategically around the room. And you can see how the calculation shows that it should fail, but with the benefit of the air cleaners plus the value you got from the 832 cubic feet per minute of clean air coming from the basic system without the air cleaners in it, you notice that it passes on a test plus mitigation basis, whereas it's failing on just a straight calculation basis. And what we found, though, is the HEPA filters, you probably should take a test afterwards, because placement and the efficacy of where they're placed and how they're operated needs to be evaluated after they're in there, if you're running on a test basis, in our opinion.
Right. And so I think when you look at that, and then when you look at the last column where it's the CFM was bumped to 250, where it passes both, you can see that the math calculated is only 1371. If you go, let's go back to that assessment where the first number is 371 total equivalent clean air, MERV 8 filter, that's really your outdoor air. The test that was done in the space gives you 832. And the reason is in the standard, as a MERV 8, we count 0. It doesn't mean that it actually does capture 0, but that's what we're accounting for in the standard. But in the in situ test that's done this way, you're getting the full effect of outdoor air plus filtration plus whatever. Now understand, that's equivalent. If you buy an in-room fan filter air cleaning system that has MERV 8 filters or MERV 9 filters and other technologies, they test that entire system as a whole, and those components would also count towards it. So I just want to make sure that it's not some sort of adjustment or sleight of hand. It truly is the same that we're treating the other air cleaning systems when they're tested as a system. And that's what we're doing with this, is we're testing this as a system in the space. So that's the classroom example. I think we move on now to
the ER.
ER. Bill?
Yeah, so in a hospital situation, the waiting areas are, as everyone knows, they can be problematic. So the effective air change or clean air delivery is 90 CFM per person in a waiting room, because there's some assumptions about how many infected people might be there and so on. In this case, the dimensions were 900 square feet with a 9-foot ceiling and 8,100 cubic foot volume. The HVAC capabilities were 1,620 CFM of total supply air, of which 450 was outdoor air. And again, it's a MERV 8 filter. This is kind of similar to what you would normally see in a clinic or a hospital waiting room. And the design occupancy here was 25 people. And we'll go into the calculator on this one as well.
Right, and remember when Bill was talking earlier, he said that the ASHRAE standard 241 values were to level out the level of risk, right, between different spaces. So me sitting in my office by myself is one risk. Me sitting in ER waiting room, I'm likely going to need a lot more air to achieve that same level of risk. So once again, in this scenario, all the items are blue. That we plugged it in from what Phil just talked about on the other. And you're dealing with 450 CFM of equivalent clean air, which divided by the number of the people shows you that this is not likely going to pass, and you would need to make some adjustments. The next slide, Phil shows the testing that he did.
Yeah, so doing the testing in accordance with the standard as we described, we found that we had about 1,944 cubic feet per minute supplied to this space. And again, it fails by a little over 300 cubic feet per minute. So in this case, again, it's failing both the calculation and the aerosol testing.
Yep. And then on the next one, we walk through the same thing where you're seeing the entire equivalent clean air calculator. Anything in gold is a value that was changed, right? So as you go down each column, you can see we've made some adjustments. So the first option, if you will, is going to 15 people and a MERV 13 filter, and it passes the calculator.
Yeah, that would work fine.
And then in the next one, we added some in-room UVGI with MERV 13 filters, but we kept the occupancy at 25. And this gets to the same scenario we looked at the classroom where the calculator says fail, but
the measurement plus the mitigation shows a pass. So this one should be successful.
Right. And so when we show it this way, what we're saying is and when we're saying it would pass, is it says should pass, meaning that you're likely going to retest this space again. And when you retest it after those adjustments, you would see that it does pass. And then the last comment, so then we also showed if you had more UVGI, more intensity, you would get more clean air, and so it passes both. And the last one we're showing is we've actually changed the capacity of the unit to increase the supply air, to increase the outdoor air a little bit, and go to a MERV 11 filter. And so showing just different scenarios of what can be done to try and show a pass on the clean air calculator and an anticipated pass or fail for the field testing. So, and I think that is the last example, Eric.
Yeah.
Okay, thank you guys. That was great. I know that we've gone from the beginning of this presentation going high level conceptual into pretty detailed stuff, and we understand those spreadsheets and calculators are there's a lot in there, and it may be difficult to digest, but I think one of our main objectives here was to show on a couple examples how things worked and walking you through the process. And I think Wade and Phil did a great job getting through that pretty efficiently. So we have a lot of questions in the chat. I'm going to briefly wrap here, and then we're going to go through questions, and there's some really good ones in here. So first point to just conclude on is the whole concept of equivalent clean airflow, as Bill kicked us off with, is foundational for planning, assessment, and commissioning, which Wade and Phil just walked us through. It is one of the critical concepts that guides those things. Secondly, the calculated analysis and the performance testing via aerosol tracer decay method determines if single occupied spaces are achieving the equivalent clean airflow requirements or whether adjustments are necessary. So that the kind of aperture of the performance testing is a single occupied space with then guidelines in the standard of how you would, what's the sufficient scope of testing for a building, and then the calculated analysis is addressing all the relevant spaces laid out in table 5-1 that you need to be concerned with in the building. The potential adjustments, as summarized in the action framework, really fall into three categories if you're not already compliant, which is one, adjust the engineering controls within the existing capabilities of the building and the systems. Secondly, to adjust and generally reduce the occupancy levels within the existing capabilities of the building and the mechanical systems. And third is making capital improvements to increase their capabilities. And those range from smaller type capital improvements like in-room air cleaners and UVC to more significant buying new air handling units and making significant investments in the HVAC system. To now level up to building level compliance, as I said, you do calculated analysis for all the specified areas per table 5-1, and then performance testing in 10% of the specified areas within the buildings. So, so that covers it. We now have about 10 minutes or so for Q&A. And I want to, we didn't explicitly say this at the outset, but maybe I'll direct this question to Bill, which is, so you talked about the some of the disconnects between standard 241 and then 62.1 in the CDC guidelines. But then there's this additional point of how do we even think about standard 241 and the whole extraordinary events, or when it is applicable relative to the other existing standards like 62.1, 170. You know, how does 241 fit in? So Bill, I'll direct that one to you.
Sure. Well, 241 I think of as a standard that relates to resilience. You know, we are lacking in standards that deal with unusual conditions that buildings are subjected to, and I think an epidemic of a highly infectious novel pathogen fits the bill there, but so could seasonal influenza. So the question really is, who says when you use infection risk management mode, and 241 doesn't give any guidance on that. But I think we've been hearing people say for some time that buildings ought to be viewed as being public health tools. So here's the invitation for the public health experts who define high levels of societal risk and tell us that we should be taking precautions to give signals that that buildings either must or ought to be put into a protective mode, just like they would tell you maybe it's a good idea to wear a mask. So that's kind of the highest regulatory level, but a building owner could decide to do it seasonally. I don't want to have a lot of employees sick with the nasty flu that's going around, so we're going to do this for the next 3 months when CDC is saying that influenza risk is high. And if you're a homeowner, it's entirely your decision, because nobody's coming into your house to see whether you have a building readiness plan or whether you're using infection risk management mode. So it's kind of a fuzzy issue. We may provide more guidance on it in the future, but right now that's where it sits. And one of the work items in the future is maybe to have a performance-based approach to this that accounts for the characteristics of different pathogens. Right now it's all SARS-CoV-2, and it's appropriate for that level of risk.
Great, thank you. Our experience with 241 right now has been, well, at least maybe let me know what you think about this, Bill, but there's a process that is now kicked off after the publication of the standard of how code setting bodies are going to adopt 241, and that will play out over months and years. But in the meantime, there's a lot of proactive work being done by building owners on either stress testing or preparing for the implementation of this standard that is already underway, and that can be done at any point. So, and as you said, there's still clarity that we need in terms of when infection risk management mode is actually going to be implemented. But right now, it's generally at the stage right now where people are figuring that out of what's relevant within their own buildings, and they're not necessarily being told that yet.
No, and it's really important to be prepared to do something, right? When did the pandemic start in the US? 2020. We still have a lot of owners trying to decide what they're going to do at the end of 2023. This takes care of at least that issue.
Right. Okay, so the next question we got is, can the performance test be performed in an occupied space? So I will kick that over to Wade and Phil.
So the actual test has to be done in an enclosed room. So to the extent that the people can be there, there's nothing harmful about it. But you do want to maintain a closed door and a closed environment during the time you're running the test, so that you don't include variables that are unknown, like how much air goes in and out the door. But other than that, all the challenge agents that have been mentioned in 241 are safe and applicable for doing it in an occupied space.
Great, thank you. Next question. So how can a tracer gas test be relied upon to provide real field infection control of virus particles be considered acceptable? So I guess just one technical.
Yeah, go
ahead.
So my mention of that was that the decay rate is a logarithmic decay rate, and the calculations are similar to those used for tracer gases. I did not intend to confuse the issue. We are using particle counts, and the decay rate of particle counts is evaluated using a logarithmic decay method to establish the volume of clean air that's coming in.
Got it. Okay, thanks. We got several questions on the case studies and the calculators. So since we're not answering those in real time now, hopefully Wade and Phil will be able to just reference back. But so first question, the aerosol performance test showed significantly higher ECA amount than the calculator. And I think that was on the classroom example. So maybe let's just broaden this question to, in some of the examples and the scenarios, the performance test was passing and the calculated value was not, or vice versa. Do you guys want to talk about resolving those types of differences and how to think about those, of what ultimately is considered passing? Do you have to pass both, or what happens if you're passing one but not the other?
Yeah, so the calculator is intentionally conservative, right? And it's following exactly what is in the standard. So if you have a MERV 8 or a MERV 9 or a MERV 10 filter, you get 0 credit for it. In reality, we know, and there's a chart that everyone has seen for filters done by someone who's on this call named Bill, that shows that it'll actually remove particles of all various sizes, even at a MERV 8. In the calculator, we're not accounting for that at all. And it can play a big part. But when you're doing the in-room testing, the tracer testing, that filter gets to actually remove particle sizes, remove particles of the sizes that you would expect, and you'll see a benefit. I think that statement, and that really gets back to, and this is Bill, if you want to expand on this at all, which is why MERV 11 was caught. It wasn't necessarily because this isn't for SARS-CoV-2. It wasn't the concern of if the particle is bigger. It's what if the next infectious aerosol floats around naked and is 0.01 micron, right, Bill?
I think from a prescriptive point of view, there was just a desire amongst the group that drafted that part of the standard to set some floor. We know we keep going down and it'll do something, but they get worse and worse at the smaller particles, and so we set it at 11. And then this discussion is really, it's kind of the difference between prescriptive and performance requirements. Prescriptively, we're not going to give you credit for anything lower than the number of 11A, but if you actually test, then you get credit for what's ever there, because how can you take that out of the picture anyway? You'd have to remove filters that were normally in place, which doesn't make any sense.
So related to this line of questioning, and it gets to how things are addressed in the calculations and the testing, there are some people commenting about, well, we're over or underweighting the filters, and then some questions around how does UVC get tested? And that was when on one of Phil's slides explicitly mentioned is not something that the standard currently provides performance testing for. Any thoughts on just like how you all within the committee thought about weighting the different controls, and then also how capabilities of testing limited, what you are able to do and what ended up in the standard?
You need to look at normative appendix A, which is all about testing air cleaners. And it fills in chamber test requirements for any type of air cleaner that works in the space, with the air cleaner that's in the space, which could be an ionizer, it could be upper room UV. It also addresses duct mounted air cleaners that work in the space. So if you put a PCO device in a duct and that puts reactive species into a space, that's covered. I think the issue that needs to be detailed more is scaling from these tests, which have to be in at least an 800 cubic foot chamber, to spaces of arbitrary size. And that's not something that we're working on, but it's a known issue. And I think that you could do an engineered solution and probably persuade an authority having jurisdiction that was a reasonable value if it was something that's currently a gap in the standard, like for upper room UV.
Right. And I think some of that is, if there's a method of test, we're using it, right? For getting CADR, AHEM has a very prescriptive test that you have to follow. Normative appendix B, A gets into that. So if you don't have that method of test, if you don't have those things, you can test. It's not,
Yeah, 185 ASHRAE 185.1 is currently specified. 185.3 will be specified as soon as it's actually published, which is a chamber test, and then AHEM AC1 and 5 are referenced. So we're diligently trying to pull together procedures that will allow you to answer these questions for any technology.
Great. Well, we are at time, and there are more questions. So I guess just a couple closing points here. First, everyone's email addresses are up here. So what we're going to do is the questions that came up in the chat, we will email back those people as best we can to give them answers. And then for anyone who wants to follow up with any of the panelists, you have everyone's email addresses up here, and please feel free to reach out. Additionally, just closing note from the SafeTraces side. So we will be doing monthly educational webinars for the rest of this year, and then into next year. Just to give you a sense of the topics that we're going to be addressing, next month will be focused on UVC and better understanding this category of technologies, and then industry focused webinars on healthcare and education for November and December. Additionally, we have certification trainings on how to use our technology, both for general application. We have an upcoming online training next on September 22nd, coming up soon. And then we have in-person training for people in the healthcare and pharmacy cleanroom testing arena next week in St. Louis. Contact information and registration information is there. And I just want to close out by thanking our panelists for making time amidst their busy schedules, and also all the hard work and hours they put in developing the standard. Thank you so much. And for everyone who attended today, thank you for listening in. And hopefully this was helpful. It's a complicated topic and we didn't do full justice to it in an hour, but we will send out a recording of this. And again, please follow up, and I'll flash up those email addresses again if you have further questions. And thank you so much. And that will formally conclude this.
Okay, thank you.